Hello everyone, welcome to my YouTube channel, SGKmistry Lectures. In this video, I'll be giving a brief introduction on the topic of crystal field theory. So I have already explained about valence bond theory, about how the bonding occurs within the coordination compounds, how the ligands interact with the central metal atom. So all these things I've already explained in my previous video. So in this video, I'll be giving the introduction about crystal field theory and how this theory explains about the interaction between the ligands and the central metal atom or the central metal ion to form the coordination compound. So now this theory was proposed by the physicist Hans Bethe, and it was proposed in 1929, and later there were modifications that were made for this particular theory by Van Vleck in 1935 in order to explain about the covalency that is present in the interaction. So first it was only proposed as ionic interactions between the ligands and the metal ion, and then there were some modifications that were made. And now we know that the coordination bond is what is formed between the metal as well as the ligands. Now, before understanding the details of this particular theory, we have to understand first thing about the shapes of the d orbitals. Now, we know that there are 5 d orbitals. So, usually when we are talking about a metal atom or a metal ion, so already we have discussed about this in valence bond theory in detail about what happens to the electrons that are present in the d orbitals of the metal atom or the metal ion. So now, in the beginning, in the absence of ligands, all these 5 d orbitals will be degenerate. Now, what is this degeneracy? Degeneracy is nothing but all of these d orbitals will be having the same energy. Okay, but when the ligands come towards the central metal atom, okay, it may be when we are talking about complexes, it can be a tetrahedral complex, square planar complex, where there are 4 ligands that are there, whereas when we are or 4 ligands or 4 pair of electrons that are forming the coordinate bonds with that of the central metal atom, or when I'm talking about octahedral complex, of course there are 6 coordinate bonds that are formed. So now, in the presence of ligands, what happens to these d orbitals? They are split into 2 sets. Okay, so now when I'm talking about d orbitals, there are 5 d orbitals. So let me talk about the coordinate axis, okay, x, y, and z. So when I'm talking about the coordinate axis, so let me take it as x-axis and this, let me take it as y-axis. Now, the d orbitals, which is the d orbital which is oriented in this direction, that is in between the y and the x axis. So here you can see the lobes are oriented between these two axes. So this is called as dxy. Okay, now we know that all these coordinate axes, they are perpendicular to each other. They are mutually perpendicular to each other, x, y, and z. So now for simplicity, let me take this as z and this as x again. So now, so let me repeat why I'm taking it as z here, because all these 3 axes, they are perpendicular to each other. Okay, so I can take it just for simplicity when I'm showing it in 2D, in the 2-dimensional way here, as I'm representing here. So I can take x and z or x and y as the axes, so that it is easy for us to understand. Okay, so x and z. So if whenever the d orbital, whichever d orbital is oriented in this way, that is in between the x and the z axis, so that orbital, that d orbital is named as dxz. Okay, and we have one more d orbital which is again oriented between the 2 axes, that is in between the 2 axes y and z. These are the 2 axes, and the d orbitals, the lobes of the d orbitals are, d orbital is oriented between the y and z orbital, then we call that d orbital as dyz. Okay, so this is about the 3 d orbitals. There are 2 more d orbitals. So how are they arranged? What are the lobes of these d orbitals? How are they arranged? Okay, so now, so if this is x and y again, okay, so the d orbital which has its lobes that are present on the x as well as y axis. Okay, so here, suppose now if both the lobes of the d orbitals, you can see here the lobes are arranged on the axis. Okay, so that d orbital is called as dx square minus y square. And there is one more d orbital. Suppose this is the z axis. So it is arranged on the z axis. So here you can see this is dz square. Okay, so these are the 5d orbitals. So based on the arrangement of the lobes, we have these different d orbitals. Now, when we are talking about the crystal field theory, first thing is we have to consider these d orbitals of the metals that is present in the metal atom or the metal ion, the central metal atom, of course, and how they interact between the ligands, how the d orbitals, how the electrons that are present in the d orbitals, how they interact with the electrons of the ligands. And I hope you remember what are ligands. Ligands, they should have at least one pair of electrons so that they can form a coordinate bond with the central metal atom. Now, let us look into the assumptions. Okay, what are the assumptions that are what are the assumptions that are considered in this CFT? So, first of all, according to the CFT, what they are telling is about the interactions. So, as I already told, we are considering the interactions between the electrons of the d orbit, electrons that are present in the d orbitals, as well as the electrons of the ligands. Here, what they are considering is the interactions between the metal ion and the ligands. They are considering it as purely electrostatic. So, this was the assumption that was made in the beginning. And later, of course, it was modified. But first, let us understand the assumptions that were made in the beginning. Now, when we are talking about ligands, I hope you remember the examples of the ligands. We have F minus, we have H2O, which is the aqua ligand. Okay, so this F minus is an ionic ligand, example of ionic ligand, whereas this aqua ligand is a neutral ligand, right? It is not having any charge. Now, ionic ligands are point charges. So for example, F minus or Cl minus, there are so many different ionic ligands which we have already discussed, right? Cn minus. These are considered as point charges, whereas neutral ligands are point dipoles. I hope you remember what are dipoles. So you can, in a simple manner, I can show it like this, where the charges are separated towards the opposite poles. Okay, so H2O, or when we are talking about NH3, so all these are neutral ligands. So all these are considered as point dipoles, where the charges are separated towards the opposite side, but it's not like complete separation like that of ions, but within the same molecule, the charges are separated from each other. So that is what is meant by the dipoles in simple words. Now, electrostatic force of attraction can be either of these two types. Ion-ion interaction, when there is a pause between the positively charged metal ion as well as the negatively charged ligand. Or ion dipole attraction, that is between the positively charged metal ion as well as the neutral ligands. So in a free atom, as I already told, all these d orbitals will be degenerate, or all of them will have the same energy. What are the d orbitals? dxy, dyz, and dzx, as well as dx square minus y square and dz square. All these will be having the same energy. Okay, so these, let me talk about these 5d orbitals: dxy, dyz, dzx, dx square minus y square, and dz square. So all of them will be having the same energy when we are talking about a free metal atom. Now, when the ligands are coming towards this particular metal atom or the metal ion in order to form coordinate bonds, then this will result in the splitting of these particular d orbitals. Okay. Now, when we're talking about why the splitting happens, this is mainly because of the interactions. First thing, let me talk about the central metal atom or the metal ion. So when the ligands are coming near near the central metal atom or the central metal ion, so what happens? There will be two types of interactions. Of course, the metal atom is positively charged, right? Whereas the ligands are negative or neutral. But even if it is neutral also, it will have a pair of electrons which can form the coordinate bond. So there will be, of course, force of attraction, right, between the metal and the negatively charged ligand. So this is one interaction. Of course, there will be also repulsion. Why there is repulsion? As we have seen in the valence bond theory also, much in detail we have discussed about this. So we know that the metal has electrons in the d orbitals, right? Of course, now we are talking only about the d orbitals in detail. So let me talk about electrons in the d orbitals, and we know that how the electrons will be moving to the other orbitals because of the influence of the ligands. All these things we have seen, or they may be forced to pair up. So all these we have seen. So now there can be repulsion also because electrons are negatively charged. The ligands also have electrons that will be forming the coordinate bond, so there will be repulsive force also. So the interactions can be either attractive force or repulsive force. Okay, now we should consider the fact that the ligands will surround the central metal atom or the central metal ion, so that the repulsion between these particular point charges will be minimum, because we know that lower is the energy, the stability is higher, right? So always we should see that stability should be more, so of course the energy should be minimum, so the repulsive forces should be minimum. So now, as I already told, all these d orbitals will be degenerate. When the ligands approach, what will happen is these three d orbitals in which the lobes are arranged between the axes, they will have lower energy, whereas these two d orbitals where the lobes are present on the particular axis, okay, on the x and the y axis in dx square minus y square, as well as on the z axis in dz square, the orbitals in the z square d orbital. So we know that here these two will have higher energy, and here you can see these three will be having lower energy. Now, why only these two will have higher energy? We know that in dx square minus y square and dz square, these two d orbitals, the lobes are arranged on the axis, and the ligands are also approaching the central metal atom along the axis, okay, or in the direction of the axis. Okay, so now what happens in these three cases? The lobes are in between the axis, right? I have already shown it to you in the beginning. So now what happens here? The repulsion experienced is minimum. The repulsion experienced by the electrons in these d orbitals and the electrons of the ligands is minimum here. It is minimum, right? Whereas in case of these two orbitals, the electrons are present in the axis, in the direction of the axis itself, and the ligands are also approaching in the direction of the axis. So here it is maximum, right? The repulsion will be maximum. So because of higher repulsion, this will have higher energy. Okay, I hope this is clear now. Let us now move forward. Let us try to understand this in much detail. One second. Yes. Yeah. So now we have to understand what is meant by the crystal field splitting. So of course we have discussed about all these things, like how the splitting takes place. Let us understand the term that is used for this purpose. Okay, so here first of all, as I already told, all the d orbitals are having the same energy, okay, in the atom before the ligands are approaching the central metal atom or the central metal ion. All these d orbitals will be having same energy, dxy, dyz, dzx, dx square minus y square, and dz square. Okay, now what happens when the ligands approach? As I already told, these will split into two different sets of orbitals. Okay, two orbitals will have higher energy and three orbitals will be having lower energy. So dxy, dyz, dzx will have lower energy, whereas dx square minus y square and dz square will have higher energy. Okay, and this difference in energy is represented with delta. So even in delta, we can talk about tetrahedral splitting as well as octahedral splitting. So suppose if we are talking about the tetrahedral splitting, then we call it as delta T, then for octahedral delta O. But about tetrahedral and octahedral splitting in detail, I'll be talking about later. But for now, let us talk about the now whatever I have explained, it is with respect to octahedral complex. About tetrahedral complex, there is some change about how the ligands are approaching. So that I'll be talking about later. Okay. So now I hope it is clear for an octahedral complex when 6 ligands are approaching. Okay. So when I'm talking about the axis, okay. So if I take this as X and this is Y, the Z axis will be perpendicular like this. So this I'm showing it in a 2D structure like this, 2D way. But just imagine this axis, the Z axis, whatever I have shown, it is perpendicular to the plane of this particular plane, wherever I have drawn it. Okay. So now, since I'm talking about the octahedral complex, we know that there are 6 ligands, right, in the octahedral complex. So one ligand will approach from here, 2, 3, 4, 5, and 6. Okay, so 6 ligands will be approaching in the direction of the axis. Direction of the axis. Okay, in the direction of the axis itself. So because of this, what is happening? There is splitting of the d orbitals. But in tetrahedral complex, it is different. That we will discuss later in detail. In my next video, I'll be explaining about how the splitting occurs in particularly in octahedral and tetrahedral complex, what is the difference and how to identify the distribution of electrons in various complexes. Okay, so this is about crystal field splitting. So now let us talk about the factors affecting this. Okay. Yes. So factors affecting the crystal field splitting and the magnitude. So what is meant by magnitude here? So as I already told you, the 5 d orbitals will be like this, degenerate. So in an octahedral complex, the 3 orbitals will be below, that is dxy, dyz, dzx, and here dx square minus y square and dz square. So these were already degenerate here, yz, dzx, dx square minus y square and dz square. Okay, so now this particular delta, whatever is there, so this magnitude, the magnitude of the crystal field splitting energy, which is nothing but delta, so it depends on various factors. So what are the factors? First one is oxidation state of the metal ion. So more is the oxidation state. Suppose if it is +2 and +3, so of course when the metal ion has a +3 charge, in that case the magnitude of delta is higher. Okay, next is about the nature of the metal ion. So when a metal is present in the 3D series and when you compare with the metal of a 4D series, then here you can see that delta increases from 3D to 4D series. Okay, so when the metal is present, when you compare these metals of the 3D and the 4D series, the one with 4D series, the metal with which is present in the 4D series, in that case, in that complex, the delta value will be higher. Next is the number and geometry of ligands. As I already told, in tetrahedral and octahedral complex, it is different. In tetrahedral complex, the delta value is lower. Okay, so you can see delta T. Delta T is nothing but the delta of the tetrahedral complex. It is equal to 4 by 9 delta O. So delta O is nothing but the delta of octahedral complex. Okay, so delta T is of course lower. Why it is lower? I hope by now we can understand why it is lower, because the number of ligands in a tetrahedral complex is less, right? There are only 4 ligands. So of course the repulsion is lesser. So of course the delta or the crystal field splitting energy also will be lower. Okay. Next is about the nature of ligands. So there are certain ligands which will bring about a larger splitting, okay, greater extent of splitting of the d orbitals, whereas there are certain ligands which will only cause a lower extent of splitting of the d orbitals. So let us talk about more about this particular point, the nature of ligands. So there are strong and weak field ligands, what we call as. So now, how do you decide which ligand is a strong field ligand, which ligand is a weak field ligand? So we have something called as spectrochemical series. So according to this series, the ligands are arranged in a particular order based on which you can decide which one is a stronger ligand, which one is a weaker ligand. So let me give you the series. So here we have sulfide ligand, so iodide, bromide, sulfide, thiocyanate, thiocyanate 2 ligand, what we call as. Okay, so these are the different ligands that we have, and these are arranged in the means of, one second, yeah, OH minus. Let me continue here. Oxalato ligand, O minus 2, aqua ligand. Then we have, so these ligands, whatever the arrangement is there, so this is based on how they split the d orbitals when they are present in a particular compound, okay, in a particular coordination compound. Okay, so here you can see this is just an arrangement which is called as the spectrochemical series, arrangement of ligands based on how they can cause the splitting of the d orbitals, to what extent they can cause the splitting. Okay, so you can see in this, very simple to identify. So here you can see carbonyl ligand, the CO ligand is having the highest level of the splitting, right? It can cause the splitting to a higher extent when it is present in a particular compound. Okay, and I hope now you can connect with that of the valence bond theory. So there also I have told, in case whenever there is carbonyl ligand or cyano ligands, then the electrons are forced to pair with each other, right? So that is, you have to bring that thought here, but here the explanation is a little bit different. So let us talk about how exactly it causes the splitting. In my next video I'll be explaining about that, but for now try to understand and remember the main, especially the important ligands, which are usually they are found in different complexes, how they are arranged, and what is their position in the spectrochemical series. So here you can easily see iodide. It is placed here, which is showing that whenever it is present in a particular compound, it causes the splitting to a very lesser extent. Okay, so here these ligands, when I'm talking about these ligands which causes the splitting to a lesser extent, they are called as weak field ligands. Weak field ligands, whereas these ligands especially which cause a higher extent of splitting of the d orbitals, they are called as strong field ligands. Strong field ligands. Okay, I hope it is clear now about what is crystal field theory and how the splitting of d orbitals takes place in the presence of ligands. And already I have explained about how the splitting of d orbitals takes place in the octahedral complexes, and then about the spectrochemical series and how do we decide whether a ligand is a weak field ligand as well as a strong field ligand based on their positions in the spectrochemical series. So in my next video I'll be explaining about how you have to distribute the electrons during the octahedral splitting as well as the tetrahedral splitting, and how do we decide about the magnetic property as well as the other properties of the metal, like whether it is a high spin complex or a low spin complex, etc. Okay, so thank you so much for watching the video. Subscribe my channel for more such informative videos.